Yesterday I tried to set the stage and introduced Schrödinger operators. So they act in L2 of Rd, and then said that one often also considers the discretized version where often the minus sign is just dropped. And so just to repeat basically what Barry said this morning, his mini course on orthogonal polynomials is actually very closely related to Schrödinger operators, and it really sort of arises in a natural way as follows. So let me just repeat that. So what you do here is you take d equal to 1 in the discrete case, and then the operator just looks like this. So the Laplacian just takes psi n plus 1 plus psi n minus 1, and then the potential acts by multiplication with Vn. Okay, so this is the operator in L2 of Z, and then you pass from Z to Z plus. Okay, so basically it's the same expression, but the n is restricted to the right half line. And then you're sort of missing one term, right? If you look at the leftmost point, you're missing the value of psi to the left of it. You just set that equal to 0. That's sort of called Dirichlet boundary condition. And so it's basically a discrete Schrödinger operator on the half line. So you have this object on L2 of Z plus. And then when you study it, you develop tools and so on and so forth. And as you do so, you actually realize that everything you do would work equally well if you were to put some coefficients here in a self-adjoint way. So if you put an an here, you want to put an minus 1 here. So first of all, you pass to a z plus, and then you introduce these off-diagonal terms, and then you call it J for a Jacobi matrix, and then maybe you call it, I don't know, an plus 1 you put here, plus an cn minus 1. And so for Jacobi matrices, the V all of a sudden is called B. Okay, but that's really all that happens. So you introduce these off-diagonal terms. And as I just said, so generally the direct spectral analysis for these operators extends to these operators. And well, once you understand the direct spectral problem, how to understand the spectral measure associated with this operator given the coefficient sequences A and B, you also want to answer inverse spectral problems where you're given either the spectral measure or some partial information about it, and try to extract as much information about the coefficients that it comes from, or the class of coefficients leading to measures with the properties that are prescribed. So well, and the connection between these Jacobi matrices and the measures you can see in various ways, and the way that was discussed this morning is via orthogonal polynomials. Okay, and the measures here associated with these self-adjoint operators live on the real line. So that's why it's the OPRL theory. So this really is this correspondence between Jacobi matrices and measures on the real line. And so there are various one-to-one correspondences. The one that was emphasized this morning was Jacobi matrices with bounded coefficients and measures on the real line with infinite support, but bounded support. Okay? And so basically there's this one-to-one correspondence. If the A's are positive and the B's are just real, the mu's are probability measures of infinite and bounded support. But there are other classes that are in one-to-one correspondence. And so this is these are aspects of the theory where you have you know, a nice correspondence between the direct and the inverse spectral problems. You can go in both directions. And so if you're looking at this, and then you ask, well, what if the measure is not supported on R? So if it's just somewhere supported somewhere in the complex plane, in general you can't do as much. However, if it's, for example, supported on the unit circle, you actually can. Okay, so that's why if you look at measures on the unit circle and form the orthogonal polynomials, they again will obey some recursion, which doesn't look like this, but takes the form that was discussed by Barry. And so now these measures on the unit circle can also be put in correspondence with suitable matrices. And so actually the matrices themselves, they haven't been mentioned yet, but probably will be soon. So they were called CMB matrices, and they take an explicit form. So these J's, they correspond to these sequences of positive A's and real B's, and these matrices C, they correspond to these Jablonski coefficients, which line the open unit disk in the unit in the complex plane. Okay, so why do I mention that? Well, eventually today I will want to actually discuss ergodic Schrödinger operators. So yesterday I just talked about general Schrödinger operators and questions that one might ask. Then I mentioned a few examples like periodic, random, and almost periodic. And today I want to embed these primary examples in the class of ergodic potentials. So I'm mentioning this because not only does one proceed by analogy here, there's really much more going on. It's really the fact that if you understand certain things in one scenario, very often, you can work out the analogs in the other scenario. Concretely, this means that there is a notion of ergodic CMB matrix. And so the general results that I mentioned today actually do have analogs in that world. So a very natural thing that you do when you look at these ergodic cases is so in this case here, to really work on the full line, but to pass from here to here, by analogy, you somehow do this half-line restriction. But then if you are interested in special cases where your coefficients are ergodic, so for example, periodic, almost periodic, or random, okay, so if these Jablonski coefficients, called alpha n by Berry, are random, for example, it's really very natural to extend from the half-line to the full line again and study so-called extended CMB matrices, right? So, and for these extended CMB matrices that are two-sided infinite, act on L2 of Z rather than Z plus, there is a corresponding theory of ergodic coefficient sequences. Okay, so occasionally as I go along, I will actually make reference to these cases. I should emphasize that this is really for reasons of personal taste. Much of the discussion will be in this case, little L2 of Z, but I will always say which of the results extend to higher dimensions, to the continuum, or to CMB matrices. All right. So then yesterday I discussed these primary examples. So periodic, well, almost periodic, and random. And I actually didn't get very far, so I discussed the spectrum of the corresponding operators. And I also wanted to say something about spectral measures and then ran out of time. So here we have band spectrum. So this was explained yesterday. So the spectrum consists of a union of non-degenerate intervals, like this. And here also. Okay, and so in the almost periodic case, just because you include the periodic case, you could in principle observe band spectrum. In fact, you can observe this also for non-periodic, almost periodic cases, but it's a non-generic phenomenon. So generically, you actually have Cantor spectrum. So it's a bit more difficult to draw, so basically the spectrum is nowhere dense. And so I will talk a little bit about that. And so then for spectral measures, okay. So here the spectral measures basically are, as a rule, absolutely continuous. So remember yesterday we said that if you have some, say, self-adjoint operator and some vector in your Hilbert space, then there is an associated spectral measure. And when I write AC, I'm really claiming that for all these spectral measures that one can consider, they are purely absolutely continuous, meaning they give zero weight to sets of zero Lebesgue measure. So for the random case, there's this dichotomy, d greater than, well, so d equal to 1, it's pure point, which means that all the spectral measures are a pure point. So this means that you have a basis of eigenvectors. So there's a description of sort of spectral measure types and behavior of these generalized eigenfunctions. So in this case, these generalized eigenfunctions actually are honest L2 functions. And so, well, this is known and completely understood. Then, so, I mean, so let me look at these bands here. So it's pure point throughout. And so then in all dimensions, what is basically known is that you have this pure point nature essentially near the boundary of the spectrum. So, okay, so near the boundary of these bands, you can show that spectral measures, again, are pure points. So the restriction of spectral measures to these small intervals will only have a point component, so will be supported on countable sets. And so now it depends on the strength of the disorder. So that came up in Abel's talk yesterday. If you increase the randomness, so for example, if you just multiply a random potential by a constant, you work in the discrete case, for example, raise the constant to infinity, at some point these intervals grow enough to eat up the interior of the bands, and you could, in fact, observe a pure point spectrum throughout the spectrum in the random case. But this will, for example, not happen in the continuum case where you always have high energies, yes?
Sorry, when you say almost periodic spectrum is typically counter, do you mean these1 or do you mean?
Okay, so yeah, so I'll come back to that point if I don't, remind me, but I intend to. So here, so this is just true in all dimensions. Of course, in one, it's just a part of what's known. In dimensions 3 and higher, at this order not too large, this is actually expected to, in some sense, describe the true answer, namely, there is localization or pure point spectrum with exponentially decaying eigenfunctions near the boundary, but then you transition into an energy region where you actually have AC spectrum. But this is far from known. I mean, it's one of the major problems. It's very difficult, and it's just wide open. In dimension 2, this is what's known, but the expected picture is that you have this. Again, one of the major open problems in the field. And so here, to complete this picture, the spectral measures of almost periodic guys, well, anything is possible. So this class of operators is quite rich, and so I want to just maybe demonstrate that by a brief discussion of the almost mature operator. So Barry asked me yesterday if I'm going to talk about the almost mature operator. So, well, let me talk about the almost mature operator because it sort of arises naturally in the discussion of this table here. So if you ask what kind of spectral phenomena are possible in the almost periodic sense, well, from the perspective of the spectral type, anything is possible, and that already is demonstrated in this very simple model. So it's discrete, one-dimensional, and Vn depends on 3 parameters. There's a coupling constant lambda, then there's a cosine term, and then there are 2 more parameters, alpha and theta. So lambda is the coupling, alpha. So to make it non-trivial in the sense of, well, we feel like we understand periodic potentials in one dimension completely. So if alpha is rational, this will be periodic. So we want to take alpha irrational. It's called the frequency. And the theta, that could be anything. So that actually doesn't play a really important role, but I mean, it does play some role. This is called the phase. Okay, so here's your one-dimensional potential. This describes the almost mature operator. And maybe I should actually say what I mean by almost periodic. So V is almost periodic So by definition, if its translates, the set of its translates are relatively compact. In L infinity. So this means when you start shifting around your potential, so either on the line like here or in ZD or RD in the higher dimensional setting, then any subsequence of all the translates will have a convergent subsequence. So this is what it means for V to be almost periodic, and this is a special case here. So this potential is indeed almost periodic, and so what is known? So a lot of things are known about this, and so when Barry talked about his paper listing these problems for the 21st century, so there were 15 problems. Of those 15 problems, 5, I believe, are solved now. The first that was solved was the one he mentioned about existence of embedded singular continuous spectrum for decaying potentials. That was solved by Kiselev. The next 3 that were solved were all concerning this operator. And the 5th problem that was solved by Bogin and Klein about continuity of the density, integrated density of states in higher dimensions in the continuum case. So those are the 5 problems that are solved, and as you see, this operator featured prominently on that list, and also among those problems that are solved by now. So there are many results. So, and I will actually follow what was introduced yesterday, that we focus more on results and what's going on and less on names. So I also apologize to everyone whose name is not mentioned. There were many, many people who contributed to these results on the almost Mathieu operator, and I'll just focus on the results and leave the credits implicit. So there are sort of 3 primary groups of results. So one is the Cantor nature of the spectrum. So under these assumptions there that lambda is non-zero and alpha is non-rational, it's just true in absolute generality that the spectrum of this operator is a Cantor set. Okay? So, but before even discussing that, let's look at the spectrum of H. So it does depend on 3 parameters, but it's not hard to see that it actually doesn't depend on the phase. So you could write this as sigma lambda alpha. It really doesn't depend on theta. That's an easy exercise using strong approximation. And so this set here is a Cantor set. And what do I mean? So that means, so in this context, for subsets of the real line that are sort of by definition compact, I mean, because it's a spectrum of a bounded self-adjoint operator, it is a compact subset of the real line. It does not contain any intervals or isolated points. Okay, so when the first examples of Cantor spectra were found in the early 1980s, this was sort of a surprising phenomenon because all the sort of classical atomic models, their spectra look quite different. They consist of nothing else but intervals and isolated points, right? So if you start from the periodic theory, you have these band spectra, unions of intervals. But then if you have impurities, local perturbations of these guys, that may introduce some isolated points outside of these bands. So you have a union of bands and isolated points, and those are typical spectra at the time. Maybe sort of decaying perturbations of periodic potentials. But here you have spectra that have neither intervals nor isolated points. So it's sort of some exotic spectral behavior, from this sort of old perspective. But nowadays, I think it's sort of accepted that this is a reasonable type of spectrum, but anyway, it's true that it occurs here. The next thing is that the measure of the spectrum is also understood, and this is also true for all parameters. So it's 0 for lambda equal to 1, And other than that, it behaves in an affine way. Okay, so here's lambda. Here's the Lebesgue measure of sigma lambda alpha. And if lambda is 1, it's 0, as I just said. So that's the so-called critical case. And for lambda equal to 0, you just have the free Laplacian. You have no potential. And the spectrum of the free Laplacian is minus 2, 2. And the measure is 4. So for lambda equal to 0, you get 4. And so if you just remember those 2 points and the statement that it's affine otherwise, then you get the following graph. So this is what the measure of the spectrum looks like. And so for positive lambdas, that's the formula. Okay, so that's the second result. The third result is exactly what it demonstrates that any spectral type is possible. So if lambda is less than 1, again, it's always assumed positive, then all spectral measures are absolutely continuous. Okay, so this would be the spectral type that you know from the periodic case. Well, if lambda is equal to 1, well, so let me be a bit short here. Are singular continuous? So this is true. So again, so if I fix my lambda, I still have the other two parameters, alpha and theta. And so if I want this statement, it's conjectured to be true for all alphas and thetas, but it's known for all alpha and all but countably many thetas. Okay, so the exceptional set is countable for each given alpha. But it's really conjectured to be true for all alphas and thetas. And for lambda greater than 1, I have actually much too little space here to do it justice, but okay. So originally the conjecture was that in the supercritical case, you have pure point spectrum, which would be the spectral type of the one-dimensional random case. And it's true for almost all parameters. So let me abbreviate a little bit. So pure point spectrum for almost every alpha, and this refers to Lebesgue measure and also the next almost every theta. And in fact, the exceptional cases are explicit for both parameters. And so they are explicit full measure sets for which it's known. And then it's singular continuous for, there are two types of results, all alpha and generic theta, or generic alpha and all theta. Generic means dense G delta set, but by this result here, these will be zero measure dense G delta sets. Okay, so there are, you can't really improve this from a measure perspective. So you have full measure set, but you will never get the full set of either frequencies or phases because of these results. But to emphasize, you see AC spectrum, you see singular continuous spectrum, and you see pure point spectrum. So in this simple family, you can already see that within the class of almost periodic potentials, any spectral type is possible. But in this model, actually, the spectral type, whenever it's known, is always pure. So in this family, you never see any mixed spectra. I mean, the only exception could possibly hide here, but it's not expected to do that.
It could also be exception.
That's true.
Supercritical.
Okay, no, but I think people are pretty close to I mean, Yo and this Chinese group, right?
But
Okay.
But
From a pure results statement
results,
perspective,
that's
yes,
also
that's true.
technically
Okay, but it is true that all known results are about pure spectral types.
Yes.
Okay, so this is the spectral types in the almost periodic setting for a specific example. Okay, so to come back to Leonard's question, well, the higher dimensional case, I mean, basically there are so few results that it's sort of way too premature to speculate about what one expects in general. I think at this point, one would just like to get some initial results to get a feeling for what's going on in the higher dimensional case. So there are some localization results for higher dimensional quasi-periodic cases. There are certainly There are. Well, anyway, there are very few results, so I'm not aware of any singular continuous spectrum in higher dimensions. There probably should be some AC spectrum. Yeah, but
There are presumably trivial, separable, higher dimensional
Right.
cases where you know this singular continuous.
yes, I agree.
Well, there is this result of Sternberg interpretation of AC spectrum and actually spectrum being non-counter for high energies.
Right. Okay. Yeah, and I'm not sure. I agree with you that one should try that, but one doesn't have enough quantitative information on the dimension of the singular continuous measures in the 1D case to infer the absolute the singular continuity of the convolution.
There are in some cases where
No.
we know that.
No. So the only case where one has quantitative information about dimensions is for Fibonacci. So in that setting, you do get,
Right.
but it's not almost periodic. So for the critical almost Mathieu, where you would like to have some information about, no, I mean, so basically in the Fibonacci case, there actually, for small coupling, there are now results where the convolution of two singular continuous measures turns out to be absolutely continuous. So it actually happens.
Sure. That
So-
that certainly can happen.
So, I mean, how do you avoid that without having good upper bounds on dimensions? So, and those are not known. So, yeah, this is actually another thing that I should mention at this point. So, whenever you have singular continuous measures, you actually want to zoom in and get quantitative information. So, you would like to know maybe the dimensional properties of this measure. So, I mentioned this briefly yesterday. So, if you have a singular continuous measure, then you want to actually look at points in its support, and you want to center balls at these points, and you want to look at mu of such a ball as a function of the radius of the ball, and that should behave like radius to some power, and so that power basically is that local dimension. And so that,
If you take supercritical,
yes?
don't we know the dimension of the spectrum is 0 by my theorem about positive Lyapunov exponent?
Yes, but
And if I take this, if I take a separable case, don't I then know that the
so I mean there's an issue about Hausdorff versus box counting dimension. So the problem is, I'm not sure that you can.
No. Two Hausdorff are still. If you take two-dimension I believe.
Okay.
But these are sets that are polar sets. They're really tiny. I'm sure they're box counting.
Oh, yeah, sure, of course, yeah. Okay, that's a good point. Okay, good. So that's some almost periodic examples. That's sort of, you know, something that one can keep in mind about these three classes of examples. Then I put this on the board. So there were some questions about notes or posting of the slides that are being shown here. So I've talked to the Institute people, and so they will try to post the files of people who give laptop talks as soon as possible, but they sort of promised end of the week. For my lectures, which are on the board, I actually could recommend this survey that I wrote. Well, I posted it in October. It covers what I do here and more. And so in addition to that, so there are books. So the standard books are Carmona Lacroix, 1990, and there's Pasteur Fegotin, 1992. And so, because, I mean, this is a long time ago, just to catch up with what's happened, well, in the meantime, there's a book in preparation on ergodic Schrödinger operators that I'm writing with Jake Fullman. So this is in preparation, but hopefully will be finished soon. So those are maybe the primary sources if you want some background on this general theory of ergodic potentials. Okay, so great. Let me now actually introduce that framework. So, so yesterday I actually talked a little bit about how these band spectra actually arise. And so in particular in the random case, not only did we see that the typical spectrum is of this band gap shape, but also that the set is the same for almost all realization of the random potential. Okay, and so this is something that you can understand in a more general perspective using the concept of ergodicity. And so if you embed these examples in the context of ergodic potentials, so this particular consequence of what we observed yesterday will become sort of natural and obvious. Okay, so I want to introduce this class of potentials. So the focus will be on L2 of Z, but everything initially extends to the higher dimensional discrete case and also to the higher dimensional continuum case, but you have to choose some framework. And so, I mean, also notationally, it's often easier to do this case, but I'll always say what does extend to higher dimensions and what doesn't. Okay, so we want to consider a class of potentials on Z that's ergodic. Well, if you know what an ergodic transformation is, and I will recall that in a moment, then basically these ergodic potentials are just obtained by sampling along the orbits of an ergodic transformation with a real valued sampling function. So that's really what it is. So these guys will be obtained as follows. So you have some transformation T. I will give definitions. And so you apply T to some point in the space on which it acts, and then actually you keep applying it both in forward and in backward time. So now you get a sequence of points in your space on which T acts, and now you want to sample with some function that goes from that space to the real numbers, because V should be real valued. So this is how these potentials will look. So let me be more specific. So omega, some sigma algebra B, and mu will be a probability measure space. Okay. Then T will be a map from omega to omega. And I want it to be bijective and bimeasurable, so measurable in both directions. And measure preserving. Okay, so bijective is clear. And so if you have any measurable set, B, then you want both T applied to B, and because it's an invertible map, you can look at T inverse applied to B. You want it to be measurable also, and you want the measures of these three sets to be the same. So mu of B is equal to mu of T of B, and then also T inverse of B. Okay, so this is what you initially assume about your space and your map, but then actually want to take it one step further and want to impose another assumption on T, namely that of being ergodic. So T is ergodic if every invariant function is almost everywhere constant. Okay, so of course, whenever I talk about functions on a measurable space, I implicitly assume that they are measurable. And so you can either work with real valued functions, but for my purpose, actually, I want to also look at the extended real line where I sort of include plus and minus infinity and look at the extended sigma algebra then. And so invariant means that f composed with T is f. Okay, so if I have that for some measurable function, then this implies that f omega is equal to some constant for almost every omega. And so when I talk about almost every omega, with omega being in this probability measure space, I mean mu almost every. Okay, So this will be the additional assumption on T. Okay, and then to define my potentials, I need this. Oh, okay, sorry. Well, I think you'll survive. So think of this as G. So I don't know. I mean, this is just a general function, but this will actually be the sampling function I'm using up there. So this I assume to be bounded and measurable. Okay, so that's my setting. I need some omega and mu and t that as a triple is ergodic. And then for a bounded measurable f, I can define my potentials v by this boxed expression there. Okay, so that's basically the definition of the class of these potentials. And so now let's just very briefly discuss why that certainly contains our primary examples. And then I'll also mention maybe one or more additional interesting examples. Okay. So examples. So of course I want to recover the three main examples. So for periodic, so how do I realize periodic sequences? So omega I just take to be a zp. Okay. So p here is a positive integer. That's supposed to be the period of my potentials. Then I look at z mod c pz as my omega. So this is a set of p elements. The sigma algebra will just be the sigma algebra of all subsets. Mu of any of the elements will be 1 over p. So that's a uniform distribution on these p points. Okay, so that's that. And obviously, if I have an invariant function, just because I cycle through all the points, if I'm invariant, I must be constant. So what?
You didn't say you cycle. You didn't tell us what t was yet.
Oh, yes, you're right. I will tell you what t is. Sorry about that. Okay, so this is my t, and now I cycle through the points. Okay, so t is that, and then so this triple or is ergodic. So this is obviously ergodic. Okay, and what is also obviously true is that V is p periodic, right? V defined like that, just because if I apply p times, that is equal to the identity, I'm back to where I started. So each potential defined like that is p periodic, but but conversely, every p periodic potential arises in this way, right? You just choose the f. I didn't tell you what f was, but any f works. Okay. So f arbitrary. Then v is p periodic, and conversely, for any given p periodic potential, I can choose f accordingly so that the potential arises. Okay, so that's in some sense a trivial example. So my next, so let me do the random case first. So the random case arises as follows. So remember what the random potentials are. You take some distribution on R that produces the value of the potential at some site, and then you use that independently at all sites to produce your potential values. So remember that, so the VNs are D with distribution mu. So this is what we want to produce. So in this framework, you can realize that as follows. So you take, so by the way, yesterday I said one of the reasons why we pass to the discrete setting is that the Laplacian becomes bounded, and also that we're often sort of interested in bounded potentials. So actually, let's assume that the topological support of mu is compact. Okay, so this is equivalent to saying that I'm looking at bounded random potentials. It's just a minor thing. Okay, so now omega, I really want to take as follows. I take this product here. Okay, I take z many copies of this compact subset of R, and therefore omega is also compact. B is the Borel sigma algebra. mu is this nu, the product measure, again taking z copies of nu. Okay, and t, well, because omega is a sequence space, right? It's by infinite sequences with elements in the support of nu. So I want to define t on sequences, so I have to tell you what the nth component is, and it's just the n plus first component of omega. So I take my sequence and shift it. It's a shift transformation. And to get sort of the true random case, the sampling function that you want to use here is the evaluation at a single entry. So take the origin, for example. If you do this, then Vn actually turns out to be, so it's f of t to the n omega. So you take your omega, you shift n times, that shifts the nth component to the origin, and then you evaluate at the origin, so you get omega n. So you really get this random sequence. Okay, and so, well, it can be shown, so I will not do this now, that t is indeed ergodic. Okay, and so the almost periodic case also arises, and it does so as follows. Okay, so so there are two directions, as in the periodic case. In the periodic case, I started with the omegas, mu's, and t's, and I used this formula to define v's, and then observed that they are periodic, and then I remarked that every periodic potential rises in this way. So the same thing happens in the almost periodic case. I can start with my definition of suitable omegas, mu's, and t's, and then observe that the resulting potentials are almost periodic, and then I will remark that every almost periodic potential will arise in this way. And so what you do here is you take a compact abelian group, well, B again is Borel. Mu is Haar measure, just because, well, if you're looking for invariant measures under the t's that I have in mind, there is no choice. So the t will be a translation. So for some fixed alpha in the group. Okay, so I fix an alpha in the group, and I just compose omega with that fixed element. That's my transformation t. Now the assumption is that t is minimal, or in other words, that n alpha, n in z, is dense in omega. Okay, so you need to find a situation where your translation actually has dense orbits. If you do that, then you want to proceed. And so now I have my transformation on my probability measure space. So this is normalized Haar measure here. And so f now is an arbitrary continuous function from omega to r. Okay? And so then you can show that v is almost periodic in the sense that I said before, namely that its translates have compact closure in L infinity. And conversely, as in the periodic case, every almost periodic potential arises in this way. So you can choose a compact abelian group and an alpha and an f, so that you're given almost periodic guy is that. And so that's slightly less obvious than in the periodic case. So conversely, if V is almost periodic, then, so you take omega, I mean, there is a natural thing that you do. So you take these translates of V, and close it in the L infinity topology. And now, of course, well, I mean, either V is periodic, and then it's obviously almost periodic, and arises, well, in this setting, which actually fits in here if you want. So let's look at the non-periodic case. If V is non-periodic and almost periodic, then all these translates are different. Okay, no translate of V is equal to V by the non-periodicity assumption. And so then really, this is an injective map from Z into the set. So Z, in some sense, maps in a one-to-one way to a dense subset of this closure. And so therefore, this dense subset can be endowed with the group structure of Z. And then you can ask whether you can extend the group structure on this dense subset to the closure. And you can. So that's the thing. So this turns out to is a compact abelian group. Okay, and so then it has a Haar measure, and so the T, so the alpha here is actually V translated by 1, if you want. So this element of omega will act as alpha. So this basically shifts V by a 1 step, and the F is again the evaluation at the origin. Okay? So now if you do this F of t to the n omega, with these choices, you recover your original guy. Okay? So any almost periodic potential arises from this construction using these choices for omega and so forth. Okay.
It might be useful to point out that every compact abelian group is a product of circles and
finite
ZPs.
ZPs, yes, that's true. Right, so in this, yeah, so if you, anyway, so these ZPs are sort of the periodic parts. If you have infinitely many of them, you sort of deal with the limit periodic part, and the product of the circles is sort of the quasi-periodic part. And if you have sort of pure cases where you have only circles or only ZPs, this is where you recover the special cases of almost periodic functions that are either quasi-periodic in the circle case or limit periodic in the ZP, product of ZP case.
Quasi-periodic usually used for finite torus.
Sorry, you're right. Finite product of circles. You're right. Okay, so these are the three main examples. And so let me give you maybe one or two more that I like, just because there are some really challenging problems that are still open, even though they arise in a quite simple way. So 4 is sort of a generalization of 2. So omega b t mu even as in 2. Okay. But so the thing is, if you don't take this special sampling function, then you get into a whole world of trouble. I mean, the general continuous function. Okay. So this is not easy. So I mean, so basically you lose the independence of these guys, right? So initially you have these independence between the potential values at different sites. That's gone now because F connects if F depends on, say, so if it only depends on finitely many entries, there's still some hope and you can do many things. That's called the locally constant case. But if F really depends on all entries of omega, then you have long-range correlations, and then it's not so clear what you can still do. So, and you can generalize that even more, can be generalized further. So this is maybe not as interesting, but still it's sort of natural, by replacing the full shift. Full shift means that I take all sequences here, right? So at each coordinate, I can take any element in sub nu. you can replace that by, say, a topological Markov chain where you have allowed or forbidden local configurations, or you have allowed transition from one step to the next or something like this by, for example, a topological Markov chain. Topological. And then maybe you want to take for mu a measure of maximal entropy or something. Okay, so there's not much work in that direction, but it's a very natural generalization. So especially if you come from this general framework, this is a really special case. I mean, from the perspective of the general framework, you do want to understand what you get for general sampling functions. It's just that the entire random theory initially goes out the window. So that's somewhat unfortunate. Okay, so that's 4. And 5 is the skew shift, which is a simple model, but which is interesting because it leads to very challenging problems. So the skew shift, so by the way, here in the almost periodic case, so in the almost mature case, so almost mature, so omega, there is, well, it's a compact abelian group, but it's one circle. Okay, so this is omega there. Mu is Lebesgue measure, again Borel, and T, omega. Actually, I called it theta there, so let's call it theta. Okay, so my point on the circle is denoted by theta, and the I just add an irrational alpha, and F was just 2 lambda cosine 2 pi theta. So if you take these choices, then the V is defined by my box, which is not there anymore, will give you the potential of the almost mature operator. So in other words, these irrational rotations of the circle give rise to very simple quasi-periodic potentials, namely those where the group just consists of one circle. Okay. Okay, so the skew shift is a simple one-dimensional extension of the rational rotation of a circle. So omega here is T2, which is R2 mod Z2. And again, alpha will be irrational. And T and mu, so it's always Borel, so I will not write this every time. Mu will be Lebesgue measure. And T, so now I have 2 components, and in the first one I just rotate as before. Okay, so in the first component I just have this irrational rotation, nothing else. The second component actually depends on what the first component does, and that's why it's a skew product with a shift, or sometimes called skew shift. And so you take omega 1 plus omega 2. Okay, and then you take F as usual, some function, so here it's not so clear, some function on omega. Okay, so here you could think of various things. I mean, for the general concept, you only need bounded and measurable. You could put continuous functions here, differentiable functions, infinitely differentiable functions, analytic functions, and that all will give rise to questions. Very, very few of them have answers. So the reason why this example is interesting is that from this perspective here, this example would fit in somewhere here in some sense. Okay, so from periodic you go by generalization to almost periodic, and so I mean these almost periodic guys are still quite close to periodic ones just because well, translates are not necessarily equal to the original guy, but at least these subsequence of translates will have convergent subsequences. So this is pretty close to periodic, whereas random is pretty far away from it. And then you see here that as you sort of increase non-periodicity or randomness, you increase the singularity of the spectral type. Right? You start off with AC here. Here, anything is possible, but for the almost material we saw that if we run this coupling constant from 0 to infinity, we start out AC, right? If it's 0, it's periodic because it's 0 potential. You turn it on, you stay almost periodic, but then when you reach 1, you're all of a sudden singular continuous. I mean absolutely continuous below 1. At 1, you're singular continuous, and then you increase further, and then your point, which is the same type as in the random case. Now, this skew shift is still pretty close to this very simple, almost periodic, almost material, for example. So you would think maybe it's more like that on a results level. And in fact, many of the tools that have been developed in the quasi-periodic case actually do extend to the skew shift case. However, only those tools that establish localization. Okay, so what you can do is sort of mimic the localization proof for quasi-periodic potentials in the skew shift case. However, what that gives you is not entirely the complete picture, because in the quasi-periodic case you are localized in the high coupling region, and so the first result you prove is localization for the skew shift for large coupling, so that's fine. But the point is that the conjecture is that localization holds for all couplings. Okay? And so this you just will not be able to prove by extending work that was done in the quasi-periodic case, because the result just doesn't hold there. Okay, so the huge conjecture here is, so conjecture, so there are many conjectures, but maybe one of the most intriguing ones is if, for example, f of omega 1, omega 2, right, so this is my f, so you take something like the almost matière. But of course, you need to explore the second component, because if f only depends on the first component, you get the quasi-periodic case back and nothing new happens. So it has to depend on the second component. So again, take 2 lambda cosine 2 pi omega 2, for example. Okay, so this would be the same sampling function as in the almost matière case. But now if you look at what you get here, if you iterate t n times, here you get n alpha. But because whatever you get here, you stick in here, you sum up these n alphas, and as you sum them up, you integrate that, and so after n steps, you get n squared alpha, or n squared over 2 alpha in the second component. So we get something like the almost matière, it's just that the n alpha is replaced by n squared alpha, which looks like an innocuous change. However, for this case, the conjecture is you have localization. So again, say for Diophantine alpha, I mean that's not really the point, for all lambda positive, which is sort of the random type result. So even in the small coupling region, are you completely localized, something that's entirely not true in the quasi-periodic case, something that's conjectured to be true here. And this is really pretty much wide open. So there is some work by Helge Krüger on several aspects of these questions, but overall, I mean, it's essentially open and quite intriguing. So that's why I sort of mentioned this model as a model that is formally quite close to the quasi-periodic situation, but on a results level is conjectured to be very close to the random model.
What about localization in example 4?
Yeah, so exactly. So so this is a sad story that I am not telling for the first time. So there's work in preparation. So this is, so since I don't mention names, I shouldn't here, but this is joint work with Avila. But since it's so sad, I just, though, let me embarrass myself again, since 2004. I mean, we have written quite a number of papers, but that was actually the first project when you visited Caltech for the first time. That was the first thing we discussed. And so, anyway, so in this setting, we feel like we have a localization proof.
Uh-oh.
Well, let's see. No, I mean, so you have to be careful. So if you just put C0 here, generically everything goes out the window. So you need always more than C0. So of course here you have no differentiable structure, but you can, excuse me, talk about Hölder continuity here. So the minimum that you need to assume here, so to prove localization is some C gamma with gamma positive. So, and in fact the gamma is related to the amount of hyperbolicity you have in your Markov chain, in some sense. So not in the entire family here, but under suitable assumptions on the interplay between the sampling function and the entropy of your dynamical system. Well, we definitely, I mean, that's written up, have a proof of positive Lyapunov exponents away from a discrete set of exceptional energies. And then it's not written up, but we have a sketch of a localization proof based on that. So it's, but anyway, for some reason, this paper never gets finished. Okay, so I think now is a good time to take a short break. Actually, a lunch break, sorry. A long break.
A long break.
Yeah.